There are three basic types of rectifier. The first type, half-wave rectifier. It converts a full-wave sinusoidal input to a half-wave output just by using a single dial. Second type, full-wave center-tapped transformer rectifier. The output is a full-wave rectified signal. It uses a center-tapped transformer. Third type, full-wave bridge rectifier. The output is a full-wave rectified signal, and these four dials are the key components of the bridge rectifier. So these four dials is called a bridge circuit. This type of rectifier is most commonly used. Let's see the detail of the first type, half-wave rectifier. It converts the full-wave sinusoidal input to a half-wave output. Since the output voltage is always larger than or equal to 0, so the current flow through the output load is always in one direction, from the top to the ground. The output current is not an alternating current. And the output voltage can be described as pulsating DC voltage. Why pulsating? This is first pulse. Start from here, second pulse, and so on. During the positive input cycle, the current flow out from here of the supply, go through the dial, go through the load resistor, through the ground, go back to this terminal, the supply. Since current is proportional to voltage, the amplitude of this current, or the magnitude of this current, and the output waveform, both following the shape of the input waveform. During the negative input half cycle, the current try to flow out from this end, go through the ground, go through the resistor, try to go into the cathode of the dial. But that's not possible. Current should flow from the anode of a dial to go out from the cathode of the dial. So end up, when current try to go in this way, the current will be just 0, it being stopped. We can see, oh, this bar stopped the current flowing in. According to Ohm's law, the voltage across the load resistor equal to the current flow through the load resistor times the resistance. Since the current flow through the circuit is 0, the voltage across the load resistor must be 0 volt. The ground is referred to be 0 volt. And since the voltage difference across the load resistor is 0, the voltage at this point must be 0. So we say the output voltage is 0 during the negative half cycle. This is the half-wave rectified signal. The peak value is labeled as V peak. The average value of this waveform can be calculated by this formula. It's about here, the average value. Take note that the average value is not at the middle here. The formula tells you so. The average value is less than 1/3 of the V peak value. Let's take a look of this example. The peak value is 100 volt. Substitute into this formula, the average value is approximately equal to 32 volts only, not 50 volts. Next, let's see this peak output voltage, which is 0.7 volt lower than the peak input voltage. See here, peak input voltage is set 0.7 volt higher than the peak output voltage. Why? During the positive half cycle, current flow through the dial. When current flow through the dial, according to the practical dial model, we are talking about silicon dial, the potential drop, or we say the forward bias voltage of the silicon dial is 0.7 volt. So that means the output voltage is 0.7 volt lower than the input voltage. Hence, this formula. Next, we see peak inverse voltage. Peak inverse voltage, PIV. It is given by this formula. So what is peak inverse voltage? Which is the maximum reverse bias voltage. When the dial being reversed, what's the maximum voltage across here? So let's see the proof. During the negative half cycle, the dial is reverse biased. The current tries to flow this way, but blocked by the dial, so no current. Current is 0. So as we discussed earlier, current 0 means the potential difference across the load is 0. So the voltage at K is same as the ground, means is 0 volt. Voltage at K is 0 volt. Peak inverse voltage is the maximum value of the potential difference from K to A. So that is VKA maximum is the peak inverse voltage. VKA maximum is VK minus VA minimum. VK is 0, this proven here. VA minimum, the minimum voltage at this point can be seen from this curve, is negative V in P. So substitute in, do the simple math, you can derive this formula. Peak inverse voltage equal to peak input voltage. This is still a half-wave rectifier, but add in a transformer to step up or step down the input voltage. Let's say this input voltage is 230 volt. We would like to step down to 12 volt or 9 volt or 6 volt according to the requirement of the load. Another function of adding the transformer here is to isolate the primary side from the secondary side. So it will be much safer for us to handle the equipment or the electronics at the secondary side, which one with a much lower voltage and current. Let's see an example. This input voltage has a peak value of 10 volt. The turn ratio of the transformer is 2 to 1. So 10 volt will step down to 5 volts. And according to the formula we just learned, we can calculate the peak output voltage to be 5 volt, the peak secondary voltage, minus 0.7 volt. So 5 volt minus 0.7 volt of the voltage drop across the dial equal to 4.3 volts. That will be the peak output voltage.